Can you guys confirm that is the screen visible or am I audible?
సఫోలా మసాలా వచ్చి ఎన్ని వస్తున్నాయి చెప్పనా? కారా క్రంచ్ అనేవి ఒక 4 వస్తున్నాయి, కర్రీ అండ్ పెప్పర్ 5 వస్తున్నాయి.
Yeah, everyone, please mute yourself, and whenever you will ask doubt, then please unmute and ask. Feel free to ask anything. Yeah, today we'll recollect some basic concepts, some basic definitions, vector spaces, bases, and the norm, inner products, and also eigenvalues and eigenvectors of a matrix. Then we'll solve some sample problems. So, vector space V is said to be or a field. If field means set of scalars. If number one, if two vectors x and y belongs to V, then x plus y should also belongs to V. And number two, if x belongs to V, then and C is a scalar which belongs to a field, then Px also will belong to V. If these two conditions satisfies, then we'll call V as a vector space. And subspace. So two conditions satisfied. One is it's a subset of a vector space, and number two, it is also a vector space. Vector space over field F. And then we'll learn what is linear independent. We'll recollect only what professor already taught. If a set of vectors v1 to vn are called are linearly independent when summation ci vi is all are vectors and ci is a scalar, is equals to 0 if and only if Ci equals to 0 for all I. So this is the definition of linear independence. Then what is span of a set of vectors V1 to Vn is equals to summation of Ci Vi I. So for all Ci belongs to a real span of a vector space. Jayant Kumar, can you please mute yourself? Okay. So what is spanning set? Spanning set. A set of vectors V1 to Vn is called spanning set of a vector space if
Excuse me, sir.
yeah till
Sir, this is Sarita. Can you please explain first and then write? It's little confusing when you write and explain.
okay. So which one you didn't understand?
Linear
So okay,
independence, sir.
let me revise again. So first I
Thank
taught
you, sir.
about vector space. So I told that V is said to be a vector space over a field if field means a set of scalars. So a real number can also be a field. Okay, so then so if these two conditions are satisfied, then a V is called a vector space. So one condition is if X and Y belongs to V, then X plus Y should also belongs to V. And if X belongs to V and C belongs to field, C is a scalar, so then Cx should belongs to V. If these two conditions satisfies, then V is called a vector space. And subspace means it's just a subset of a vector space, so that is called a subspace. And second condition is it should also be a vector space. So VS means a vector space. So vector space means this above two conditions should satisfy, and then linear independence. That means a set of vectors V1 to Vn are said to be linearly independent when summation Ci Vi equals to give the solution Ci equals to 0 for all I. That means suppose there are two vectors. So I can give an example. Sorry, the pen is not working. One minute. Please excuse me. Yeah, so the example can be suppose this is a 0 1 vector and then 1 0 vector. So these two vectors are linearly independent. Okay, so this is the example. Then span of V1 to Vn is summation of Ci Vi. So Ci is a scalar or real number. So so this Ci summation Ci Vi is the span of V1 to Vn. Then spanning set of a vector space means V1 to Vn is a set of vectors, but when it should be a spanning set of a vector space V if V equals to yeah, if V equals to the span of sorry, the pen stylus is not working. 1 minute.
Sir, you are not audible.
Yeah, okay, thank you. Yeah, am I audible now?
Yes, sir.
Okay. So span of V, so this V1 to Vn is a set of vectors. So span of V1 to Vn is equals to summation of Ci Vi, and where Ci belongs to a real number, and the spanning set of a vector space if a set of vectors V1 to Vn will be a spanning set of a vector space if V, I mean that vector space equals to span of V1 to Vn. And so then I'm going for next topic, that is for fundamental subspaces of a matrix. So suppose let A is a matrix which whose elements are A11, A12, and dot dot A1n. So it's a M cross N matrix. So each element can be written as Aig, where I goes from 1 to M and J goes from 1 to N. So first is First is range space of a matrix. So range space is denoted by R of A. So range space is equals to, for all the y belongs to R power m. So that means it's a m dimensional vector such that y should be equals to ax for all x belongs to R power n. So this is the definition of a range space. So that means it's a mathematical definition. So that means we can write it's a span of columns of A. So that means uh, so it's a span. So suppose if I write down the columns of A, so first column is A11, A21 dot dot AM1. So this is the first column. Suppose its name is A1. Then A2 is equals to A11, A12, 22. So this is second column. So like that we have n columns. So and so this n column. So each column has length a max. So each column has actually there is some noise. One echo is coming. Actually, let me unmin. I don't know why echo is coming. Okay, so each column has m elements. So we can write range space of A belongs to R power. I mean, it's a subspace of R power m, and it has also n columns. So that's it's also a subset of n power n. So now we'll go for rank of a matrix. So that is equals to dimension of range space of A. So as it's a subspace of R power m and R power n, so it should be less than equals to minimum of m comma n. So then we'll go for second uh, subspace, that is null space. Null space of A. So it's denoted by n of A. So that is x such that Ax will be equal to a zero vector. Then x belongs to null space of A. And it is also a subset of R power n. So and one more thing is that suppose, so this is okay. Before that, so then number 3 is the row space. Row space is range space of A transpose, and 4 is left null space.
Excuse me, sir. I'm having one doubt.
Yeah, please ask.
Sir, in null space means the vector will be 0.
Huh? Can you please repeat?
Sir, in null space means the entire vector will be 0.
Not the entire vector will be 0. So suppose null space will contain x. So which x? So such that ax should be 0. So That means suppose A is a matrix who has elements 0, 1, and then 0, 2. So then, so suppose X is another vector, X will be another vector. Let's say it's 0, 0. Then suppose it's 1, 0. 0, 0, 0, 0. Yeah. So suppose let's take a matrix who has elements 0, 0 and 0, 2. So then so X will be some 1, 0 vector. So it's 1, 0. So this is a vector. So if you multiply Ax, so that will be 0. So we can say that X belongs to null space of A. So null space of A will contain those many X's, so that Ax is 0. And then left null space is null space of A transpose. It's the same, but it's a null space of A transpose. And then suppose there is a matrix A m cross n, and this is a space of R power m, and this is another space of R power n. So we said that range space belongs to, I mean, it's a subspace of R power m. So suppose this is a range space of A, and this is the range space of A transpose. Then we can show that this null space of A transpose is also belongs to R power m, and these two are orthogonal. Suppose A has rank R, so that means dimension of range space of A is the R. So it has R element R. Someone is coming. Okay. So this dimension is R. Then the dimension of this null space of A transpose will be M minus R, and here dimension is R. Then it will be N minus R. Okay. And this range space of A and null space of A transpose are called orthogonal complement subspaces. So range space of A and null space of A transpose also similarly this range space of A transpose and null space of A will also be orthogonal complementary subspaces. Okay, so this is some basic, and one more thing is that if you write down here, so here M is equals to R plus M minus R. That means R is the dimension of range space of A, plus M minus R is the dimension of null space of A transpose. So this is called a rank nullity theorem. Okay. And okay, so then we'll go for another topic, that is eigenvalue and eigenvector. So the definition is, so X is a vector and lambda is a scalar. Lambda is a scalar, so are said to be eigenvector and eigenvalue pair. If Ax equals to lambda x, where x not equal to 0. So if Ax equals to lambda x, then we can say that lambda is the eigenvalue corresponding to the eigenvector x. So Ax minus lambda x equals to 0. matrix. Then we can write A minus lambda I x is a vector, then 0. So some this is a B matrix. So then if you see that this is a Bx equals to 0, so then we can say that so x belongs to null space of B as Bx equals to 0. So that means x belongs to null space of A minus lambda I. Okay, and as okay, so then null space of A minus lambda I, that means we can say that some linearly dependent columns. So that means if you take determinant of A minus lambda I, that will be 0. Or we can say determinant, we can say like this only, is equals to 0. So this is a characteristic equation which gives the solution of eigenvalues of a matrix A. So this is the eigenvalue and eigenvector. Then we'll go for another topic, that is norms and inner products. Definition of norm. So it's a function, it's denoted by this sign. So this will go from vector space V to some real number if so there is some conditions. Number one is norm of x greater than equal to 0. This condition is called the non-negativity. So x is a vector, so it and 1a x equals to 0 if and only if x equals to 0. Number two, norm of cx equals to mod c. So this, and number three, so this is called these are called triangle inequality. So if these three conditions are satisfied, then we can say this function is a norm. So we can write down some examples like that. LP norm is equals to, we can write down x is a vector, then it's a LP norm is equals to summation of suppose x has a n elements, then we can write down this is a LP norm. So this is a norm actually. So if I put p equals to 0, then sorry, p equals to 1, then it will be L1 norm. Then p equals to 2, it will be L2 norm, like that. Then inner product. So inner product is denoted by this function. So it will go some two vector space to a real number. So and then conditions are 1 x comma. If I take inner product of two vectors, same vectors, then it will be greater than equals to 0 and 1a equals to 0 if and only if x equals to 0. And then number 2, inner product of y plus z, inner product of x and y plus inner product of x and z. But 3, suppose C is a scalar, then we can write say inner product of x and y. Then number 4 is inner product of x and y the same as inner product of y and x. So these four conditions. If these four conditions are satisfied, then we can say this function as a inner product. So we can write down example like if x and y equals to y transpose x, then okay. So this is a inner product. Okay. Okay. Now some sample problems which will be related to your assignment problems. For one, if A is a matrix, A is denoted by 2, 1 minus J, and J is a complex number, then what is A Hermitian? So we can write down this as suppose A is a matrix A1, 1. So M cross N matrix, then A transpose can be written as A1, 1. So this is A transpose. Then what is A Hermitian? That is the A conjugate transpose. That means conjugate means we will conjugate each element of A. That means same as this one, A11 conjugate, AM1 conjugate, A1N conjugate, and AMN conjugate. So then by this definition, what should be A Hermitian? So A Hermitian will be A trans a conjugate transpose. That is conjugate means 2, 1, plus J1 minus J3. Transpose of this. So if you see that it's A equals to A Hermitian. So this matrix is called as Hermitian matrix.
So how will we found that conjugate part?
Okay. So conjugate of A. So this can be found. So we can conjugate each and every element of A. So it's 2 1 minus j and 1 plus j 3. So conjugate of 2 is 2 and conjugate of 3 is 3, and conjugate of 1 minus j is 1 plus j and conjugate of 1 plus j is 1 minus j. Then we'll transpose this A conjugate, then that answer will be 2, then this 1 plus j will go to here, so 1 plus j and then 1 minus j 3. Then we can say that this A equals to A Hermitian. So if this property satisfies, then we can say A is a Hermitian matrix.
Hello.
Hello.
Sir, can you please explain whether norm and inner product that you are explaining using this sets from R to, sorry, V cross V to R and all will
Yes.
belongs to field or not? Like, is it a field
Okay,
which is having
so
these properties?
here the field is a real number. That's why sometimes I am writing R and sometimes F. So I have written at the beginning only F. After that I have changed that to real number. So we can take a real number as a field in this course.
Acha, acha. So, can you go up a little bit? This vector norm from V to R. So, but R should have some properties to be called as a field, right? We cannot say because this inner product and norm can be defined from every vector space to every other field or only R.
1 minute. Can you please wait?
Yeah.
Yeah, yeah, please tell now. Yeah, yeah.
Yeah, I'm telling that this R is called as one of the field because it is
Hmm.
having some of the properties, right? So,
Yes.
in general, can we say that norm and vectors, this inner product, are defined from vector space to any field?
Yeah, correct. To a not okay to not any field, to a field such that this three conditions should satisfy.
Yeah, yeah, yeah. These conditions will satisfy, obviously.
Yeah,
So, okay, then we can call this as a as
correct,
a norm. Okay.
correct, correct. Not
Okay.
just a real number, so it can be any field.
Okay. Okay. Thank you, sir. Okay.
Yeah, but for this case, for this course, we can take a real number as I mean field. That's why. Okay. So the second question is, suppose there are two vectors. X1 is equals to 101. X2 equals to 011. The question is number one is x1 linearly independent with x2, or we can say this way that x1 and x2 linearly independent, and second question, are they orthogonal? So for the first question, so we know that two vectors are linearly independent. So suppose x1 and x2 are two vectors, then we can write down that summation of ci xi equals to 0. That will gives ci equals to 0 for all I. So let's check here if this condition is satisfied or not. So suppose c1 x1 plus c2 x2 is equals to 0, then c1 into 101 plus c2 to 011 equals to 0. c1 plus c2, then 0 plus c2, and then c1, sorry, so c1, then c2, then c1 plus c2, it is 0. Then you can write c1 equals to 0, c2 equals to 0, and c1 plus c2 equals to also 0. So these two conditions, so all ci equals, so we can write ci equals to 0 for all I. So hence x1, x2 are linearly independent. And the second condition is, let's check it's they are orthogonal or not. So second question is orthogonal or not. So we'll check the orthogonality by using so inner product. So suppose x and y are said to be orthogonal if y transpose x equals to 0. So, and we showed that y transpose x is also an inner product. So we can write down that if y transpose x is a 0, then we can say x and y are orthogonal to each other. So let's check here. So y, so suppose here, okay, so here not y, here x1 and x2. Okay, so we'll check x2 transpose x1. What is the value? So x2 is 0, 1, 1. This is x2 transpose, and x1 is 1, 0, 1. And value is 0 plus 0 plus 1 is 1. So they are not orthogonal, not equal to 0. So and number 3, third question is, let's take x1 equals to 0, 1, 0, and x2 equals to 1, 0, 1. So are they orthogonal? So let's check x2 transpose answer. x1, that is equals to 1, 0, 1, 0, 1, 0, equals to 0 plus 0 plus 0, 0. So x1 and orthogonal. And then let's check, are they independent or not? Are they linearly independent? So answer is yes. How? So if you follow the same process, so this process, then you will see that see all ci will be 0. So it's hw check for all orthogonal vectors, there always, but the reverse is not true. Yeah, fourth question is to Suppose there is a matrix 4, 1, 1, 4. So what is the eigenvalue and eigenvector? Okay. Okay. So the solution. So we know the eigenvalue will give if so determinant of A minus lambda I equals to give this the characteristic equation. So that is A minus lambda is equals to so 4 minus lambda on 1 4 minus lambda. So lambda equals to 3 and lambda equals to 5. So these two are eigenvalues. Then eigenvectors. So to find the eigenvectors, so we'll find x. Okay. So ax equals to lambda x. So what is x? X should not 0. Okay. So let's take lambda equals to 3. Okay. Then a minus lambda. Okay. Then so a is equals to so 4 minus lambda. So it's a 4 minus 3 1 1 4 minus 3. So it's okay. So x1 equals to minus x2. So we can write down. So x can be some c is some scalar into 1 minus 1 for all. So this is a one eigenvector and another sorry. Yeah, one eigenvector and for lambda equals to 5. What should be the eigen vector? So similarly, a minus lambda into x equals to 0. Equals to 4. So 4 minus 5. So these two are same equation. If you send x1s to that side, so it will be same equation. Okay. So same equation. So it's a redundant equation. So we can write one equation. So that is x1 equals to x2. So x equals to c 2 1 1. So this is another eigenvector. Okay. So uh, eigenvalue for eigenvalue 3, it will be okay. And the next question is if A is a Hermitian matrix, that is A Hermitian equals to A, then eigenvalues of A will be real. So this is a statement. This is a correct statement. So I need to prove it. So solution. There will not be any proof in the assignment question, but still why it should be eigenvalues should be real. So that I need to show. So this is the characteristic polynomial is determinant of A minus lambda I. This is the characteristic polynomial. Okay, so then you can write determinant of, so determinant of A is equal to determinant of A Hermitian conjugate. Okay, so this is the A minus lambda I Hermitian conjugate, that is equals to determinant of A Hermitian minus lambda star I conjugate. Okay, so now for the find the eigenvalue, we need to we need to put p lambda equals to 0. So that means uh, determinant of A Hermitian minus lambda star I okay. So shows that lambda star is the eigenvalue of A, where lambda is the eigenvalue of A. So if lambda is the eigenvalue of A, then lambda star will be eigenvalue of A Hermitian. Okay, so it's A Hermitian. So then lambda star will be eigenvalue of A Hermitian. So this is one thing, and okay, and then so A Hermitian equals to A. So then lambda star should also be lambda. That means lambda is real. Okay. Okay. So then next question is 6. Question number 6. X is equals to 1, 1. 1 transpose, then find, or what should be L1 norm and L2 norm. So L1 norm is equals to summation of xi mod power 1 power 1. So all are positive numbers. So then we can write summation of I equals to 1 to n 1 is equals to 1. Okay, and then what should be the so what should be the x? What should be the L2 norm? So that will be equals to, that will be same as 1 to n 1 power half. It is root n. Question number 7. Yeah, x equals to 1 2 dot n. So n cross 1 vector. So then what would be the L1 norm and L2 norm? Yeah. So L1 norm will be same formula. So summation of y equals to 1 to n mod xi. Okay. So this is the formula for summation of n natural numbers. First n natural numbers. Then what should be the L2 norm? So this is the L2 norm. The square of first n natural number. So that's the formula is there. That is n into n plus 1 into 2n plus 1 by 6. So this is the formula. 7, 8. So suppose x is a random variable. So it's not a vector. It's a scalar. Okay. And x is a Gaussian distribution. So normal distribution with mean mu and sigma square is the variance. So it's called the mean of x, and this is the so okay. So then we can write down the uh, distribution of what is the distribution. So distribution is 1 by root over 2 pi sigma square exponential of minus okay. So this is the formula. Now one more thing is that if you put mu equals to 0, put mu equals to 0 and sigma square equals to 1, then it will be x will be standard normal distribution. Okay, and then question number 9 is
Sir, in question number 7, if we have to find norm of L0, then what will be the answer?
okay. Question number 5, question number 6, right?
No, sir, question number 7.
Oh, 7. Okay. Question number 7. What is the question?
Sir, if we have to find the norm of L0 in case of L1
Okay,
and
L0 norm. Okay. So this formula, what I have written, that is for so LP norm. What formula I have written, that is equals to, suppose this the P, that is equals to summation of. So that is for P greater than equals to 1. Okay. So that means after 1, I mean L1, L2, after that up to infinity, we can find out. Okay. But for L0 norm, we can define L0 norm as 1 minute. So L0 norm is one thing, that is so
Sir,
suppose a vector.
how will infinity norm will be defined then?
Yeah, infinity norm can't be defined by using this formula. Infinity norm also we can write infinity is equals to max of. Yeah, correct. So that P can't be infinite. So it will be more than one, but can't be infinite. So it will be some max of xi. Okay, mod of xi for all L. So for that, we need to find mod of xi, and for L not now, we need to find out the
Can you
number of
provide
non-zero
some
L.
figures for these norms like 1, 2, and infinity?
Can you
Like
repeat?
graph of these norms, like we can't visualize it. It will be better for us to visualize.
Okay, graph of all these norms.
Not all these. One I can understand. Two, how the infinity, it's a max. It will be somewhat like sorry, it will be somewhat square or what max.
Okay, fine. Okay, so then I will next day I will show you the graph of L1 norm, L2 norm, and infinite norm. Okay.
Yeah, please. Okay, thank you.
Okay, so then the next question is yeah. So for the vector random vector, so suppose say here x is a random variable. That means x is a scalar. So if I take x as a random vector, okay, then what should be the uh, distribution of f, distribution of x? So suppose it's a random vector of mean mu and covariance matrix sigma. Okay, so mean expectation of x sigma is equals to expectation of. So then we can write down what should be the, is just a one generalized equation by root over 2 pi power n, 2 pi power n determinant of sigma exponential of minus x minus mu transpose sigma x minus. Okay, so this is just a formula for random vector x. So the next question is so let x is a normal distribution with a mean mu and variance sigma square. Convert it to a standard normal distribution. So let y is also another random variable, that is as same as x minus mu by sigma. So let is another variable. Then if we found out the expectation of y, that will be as same as 1 by sigma expectation of x minus mu. Expectation of x equals to mu. And what will be the variance of y? Okay, so that will be y minus expectation of y. Is the okay. So we find out y minus expectation of y equals to 0. Okay? Expectation of y square. The expectation of y equals to x minus mu. Sigma square expectation of x minus mu square that is equals to 1 by sigma square into sigma square 1. So here if you see that the standard normal distribution variance is 1 and mean is 0. Okay, then the next question is question number 11. Is A transpose A positive semi-definite or not? So the solution is, so the to find the positive definite matrix, suppose there is a matrix B. So B is a matrix, B is said to be positive semi-definite. X transpose Bx equals to 0 greater than equals to 0 for all x. Okay, so let's check here. So suppose x is a vector, then x transpose A x is equals to x trans. So let y equals to ax. Okay, so then so it should be ax x transpose. So y transpose y, norm of y square. So norm is always greater than equal to 0 is the definition of norm. So so this is always greater than equal to 0. So A transpose A is a positive matrix. Yeah. So that's all for today. So do you guys have any questions you can ask me? So we can summarize what I taught today. So I taught the definition of vector space and what is the subspace, then linear independent vectors, and then what is the spanning set of vector space, and for some fundamental subspace of a matrix, that is range space, null space, row space, and left null space. And we showed that what is orthogonal decomposition of the subspaces. So this is called the orthogonal decomposition. Okay, and then I revised that eigenvalue and eigenvectors. So it's definition of eigenvalue and eigenvectors. Then norm and inner product. So I define what is norm and what is inner products, and give some example of norm and inner products. And sample problems I started. After that, some sample problems I solved 11 problems. So first one is some A matrix is given. That is a complex matrix. So we need to find the Hermitian of yeah, Hermitian of a not Hermitian, yeah, Hermitian of a matrix. Oh, sorry. Okay. So it's a Hermitian we need to find out. So that we found out. Then Uh, so this x1 is a vector. Then we solved that how x1 and x2 are linearly independent vectors. Then so we solved using these two. First is linearly independent, and then second one is orthogonality. Okay, and third is I gave one another two vectors which are orthogonal. So then I told that you guys can prove that any two orthogonal vectors are always linearly independent. That is the homework. And fourth question is what is the some I gave one matrix. Then what should be the eigenvalue and eigenvector of that matrix. So it's some one process to find the eigenvalue and eigenvector. Okay, and then fifth question is if A is Hermitian matrix, that is A Hermitian equals to A, then all the eigenvalues should be real. So that proof is also I have given. At first, I proved that this uh, eigenvalue of a Hermitian matrix is conjugate of that matrix, eigenvalue of that matrix. So then. X is a vector, so suppose it's a one vector, then
Can you please repeat your question like you told? All the orthogonal vectors are linearly independent, but reverse is not true, isn't it?
yeah, all orthogonal vectors are linearly independent, but reverse is not true. Correct.
Acha, okay, sir, fine.
Okay. Okay. Then I took one vector, that is n cross one vector. Then I found out the L1 and L2 norm of X, and the seventh the second after that I took one to n vector. Then what should be the L1 and L2 norm of X? Okay, and can you guys tell me what should be the infinite norm of X for this question number 7? If n is greater than equals to 0, then what should be the, and n is I mean 1 2 3 dot dot, so it's increasing only. So then what should be the infinite norm of X? So yes, you can tell that infinite norm equals so using this definition, so that should be n.
Okay, yes.
So then after that I found, so after that just it's just a normal distribution. So after that I write down the normal distribution PDF, the probability distribution function of a normal distribution, that is on 1 by 2 pi root 2 pi sigma square exponential of minus of x minus mu square by 2 sigma square, where mu and sigma square are the mean and variance of x. Okay, and if x is a random vector, suppose there are so many random variables, we stack all those random variables in a vector, then what should be the, and each random variable satisfy one normal distribution. So what should be the uh, distribution of random vector? So that is just a formula. So this is a distribution, and then suppose there is a random variable having mean mu and variance sigma square, then how to convert that random variable to a standard normal distribution? That means how to how to make one another random variable who has mean 0 and variance 1. So that is y equals to x minus mu by sigma. Okay, and then suppose there is another matrix A transpose A. So is it positive semi-definite or not? So we showed that it's a positive semi-definite matrix because for all x we can write down, we can show that x transpose AX will always be greater than equals to 0. Okay, so that's all for today. So if you have
Sir,
any question, yeah, please tell.
what about AA transpose?
Yeah, so that also be a positive semi-definite. Okay, so it's a good question. So let's take B equals to A transpose, then X transpose B, sorry, X equals to X transpose A transpose X. Now let Y equals to A transpose X. So that can be written as so A transpose X. Okay, so A transpose X, then A transpose X at X transpose, whole transpose. Okay, then it's a Y transpose Y. So normal Y square. This is also a positive semi-definite matrix.
So, the positive semi-definite matrix should be a square or not? Like it should be square matrix always.
Yeah, correct. It should be a square matrix.
But if we take this A transpose, then A cannot be square, like an M cross N, then N
Yeah,
cross N.
A cannot be square, but we are not finding the positive definiteness of A. We are finding positive definiteness
Yeah,
of
got it.
A transpose. That is a square matrix. Okay.
Acha, okay, so thank you.
Okay. So if you guys have any question, you can ask me now or after next class also you can ask me. So I will wait for 5 more minutes. Then after that we'll leave. Okay. Yeah, so this course is only for Saturday from 5 to 7 p.m. So every Saturday we'll have this TA session, that is problem solving session. So I'll just deal with some problems only. Okay, so there will not be any theory class. And I will upload this video. This video is recorded, so I will upload this video in some one YouTube channel. I need to upload. Then I will give that YouTube link actually. Okay, after that. Next online class will be on next Saturday. Okay, every Saturday we'll have this.
Sir, can you explain fifth problem?
What problem? Which problem? Sixth?
5.
Fifth. Okay.
Yes.
So A is suppose A Hermitian equals to A, then what should be the eigenvalues of A? Okay. So it should be real. We need to prove. So how to prove? Then so for that I showed that uh, if A has a eigenvalue lambda, then A Hermitian will also be eigenvalue lambda star. Will also have eigenvalue lambda star. That I have shown by taking this characteristic polynomial. So P of lambda is a characteristic polynomial that is equals to determinant of A minus lambda I. Okay. And So determinant of a matrix is equals to determinant of that Hermitian of that matrix and then conjugate of that matrix. Okay, so that is same as determinant of a Hermitian minus lambda star I, and then that should be equals to 0. So then lambda equals to lambda star. So eigenvalue of a Hermitian will be lambda star, and after that a Hermitian a equals to a. So lambda star equals to lambda. So lambda is real. So so that means every Hermitian matrix, I mean, yeah, if A Hermitian is equals to A, then that matrix will have this real eigenvalues. Okay.
Okay, sir.
Okay, guys, thank you for joining and have a good rest of the weekend.